Okay guys, welcome back. We're going to do some cool stuff now. This is 4.1 part 4 where we put it all together. Now here's where we were last time. We had values and formulas to show the displacement, the velocity and the acceleration. Now we're going to use these formulas to do some pretty cool stuff. The first thing we're going to do is realize and use the fact that there's big similarities between the formula for x and the formula for a. You'll notice that the sine omega t term in both of these is the same thing. Okay? The a at the front, okay, of this one, and the a at the front of this one. So at the end of the day, if we were going to connect acceleration with velocity, let's say we wanted to make a divided by x, you'll see why in a second, okay? Bear with me. A over x. What that leaves us with is the negative sign, the omega squared over, well, everything else is cancelled out. Okay, the a's, that's it. A over x is equal to negative omega squared. So what we've done is we've totally connected the angular velocity of this thing with what it's going to accelerate and the x value, the displacement, okay? And this is going to be a really useful formula coming up. So keep that one in mind. Now what we're going to have to do is look at the springs, right? The spring itself. Because we want to connect the actual reality of our spring and our mass, okay, to this thing. It's got to be connected somehow, right? I mean, you can imagine if we had a really tough, stiff spring, the angular velocity, okay, if we bob it up and down, is going to be very fast. If we have a soft spring, then it will be a slow angular velocity. And at the same time, if we have a really big, chunky mass, it's going to slow everything right down, okay? So we're going to have an angular velocity that's slow. If we have a small mass on the end of a spring, it'll jump up and down like crazy. So there must be a connection between the spring, the mass, and these things here, especially the angular velocity. And we're going to work that out right now. The first thing we have to know is, how does a spring work? What does it do? Okay. Now you've got to realize that a spring is can be defined by how stiff it is. Okay. And the stiffness of a spring is measured in the constant K. K is known as the spring constant. The spring constant is a measure of how stiff the spring is, or really, how hard it is to pull a spring. Now you should have a spring lying around somewhere, and you should realize that if you have a spring, let's say this is the spring's rest position, okay? If you stretch this spring and stretch it out, okay, you are going to need a force to do that. And if you keep stretching the spring even further, you are going to need an even bigger force to do that, okay? So obviously, if we have our rest position of our spring, okay, if we stretch it from that position, okay, a value of x, there's some connection between the force we need and the value of x that we get, okay? That is basically the spring constant. The spring constant tells us how many newtons it takes to stretch a spring 1 meter. Let me give you an example. Okay, a spring, if we stretch it, let's say, I don't know, 20 centimeters, 0.2 meters, okay? And then the force we feel at that amount of stretch, okay, is, and remember the stretch it, okay, that's our value for, that's our x value, right? The force we feel, which is our F, let's say that's 10 newtons. No problem. What we can do then is we can say something about the stiffness of the spring, and the stiffness is equal to the force per distance. Okay, so it's measured in newtons for the force per meters for the x. The spring constant is measured in newtons per meter. Now here's the cool thing. If we graph for different values of stretch how much force we had to apply, well, if we stretch it a little bit, we'll only need a little force. If we stretch it more, we'll need bigger force, and a bigger force, and a bigger force, and a bigger force, and a bigger force. And springs, at this stage of the game, follow a linear path between the force and the displacement. Okay? Now that gets to a certain point where you just bend the spring and destroy it, and then you can sort of keep stretching it and it's destroyed at that value. We don't worry about this bit here at this stage. That's called plastic deformation. That's when you've just basically destroyed your spring. So at this stage of the game, we're interested in this part of the graph. Now you'll notice K is equal to F over X, right? Force, which is the Y value, over X, which is the X value. Now, Y over X, rise over run, okay, the gradient of this line is K. So that's the connection between the force, the displacement, and the spring constant, okay? Another way we can write that, Y equals gradient times X. So there we are. Pardon me, this is going to be a really useful equation in just a bit. So we'll keep this in mind as well. Okay, so that's basically how the springs work. Now, if we go back up to the top, here's equation 1. A over x, the acceleration divided by x is equal to negative omega squared. Let's write that again down here, along with our new equation, and see what we can do with that. A over x is equal to negative omega squared. And now we have F is equal to Kx. Looks like we have something to play with here, because we've got x's lying around, haven't we? What we don't have over here, though, is an A. What is the acceleration and how does it connect to this? Well, hopefully, we remember, again, the force is equal to the mass times the acceleration, right? If we substitute that in, then mass times acceleration is equal to k times x. Hot stuff. Now over here we've got a divided by x. Well, that's quite easy. We just take this x value and we divide by x on this side. We divide by x on this side. We end up with mass times acceleration divided by x is kx over x. Okay? Leaving us with mass times a over x is equal to k. I'm doing this the long way, hopefully you guys can do this too. We want to get the a over x on its own so it can go and play over here. So we're left with k over m. Okay? The acceleration of our thing bobbing up and down divided by the displacement is equal to the spring constant divided by the mass. Sweet. Let's put this term over here and we end up with the following. Okay, instead of a over x here, I'm going to put k over m. So what we end up with is big red letters, k over m equals negative omega squared. Now what does that really mean? Well, here's the idea, okay? We now have defined our spring that we're using. We've defined the mass that's on the spring. And these two things, and those two things alone, will definitely decide our angular frequency, how fast our little guy is going to go up and down. Now, you are going to do, or have already done, a lab in class where we test this, okay? Remember, omega is equal to 2 pi over the period. Now what you're going to be doing is you're going to be getting an actual setup where you set up a spring on a stand and you have a mass here, okay, and you can pull this down a certain value of initial displacement or the amplitude, and then let it go from down here, and it will go up and down and up and down, and you're going to time it. The time taken for, say, 10 oscillations, so that's an oscillation is a full up and down, okay? And then you can find the period. The period is equal to that time divided by 10, okay? That's the time for one oscillation. Once you have measured the time for one oscillation, you can find out, convert that to angular frequency. Okay, so what we're going to really get here is a table of, you need to set it up in Excel, where you have the time taken for 10 things. From this you can find the period. From this you can find the angular velocity. Okay, now we are going to check that angular velocity, and ultimately we're going to be seeing if this is really true. Okay, so we are going to need to find a value for negative omega squared. So I'd like you to do this for let's make it, why not, 3 different masses. Okay, you're going to measure the masses in kilograms and go from there. Now what I should do as a good scientist on this table is also have a thing in here showing the units. This is measured in seconds, this is measured also in seconds, this is measured in radians per second, this is measured in radians per second squared. Okay, and mass should be measured in kilograms. Once you've done that, okay, we go to the next bit about testing to find the value of K, because we need that to see if this formula and the other formulas above are actually true. Cool, that's that for now. Thanks for sticking with it. Would love to hear any questions, but hopefully this is starting to make some sense. See you next time.